Okay, everyone, so we're going to just finish up the chapter 20 at the bottom here, page 102. So everybody turn to page 102. And this was just the second practice example 2 here. So also get out your iClickers because we're going to start with an iClicker question on this. So you're given this model here, and it's just a general model that has 4 slopes, a linear model here, and this E term is error. So some people were asking me about that last time, how to read this. So notice there's no hat over the y here. So this is saying y values. The y values are equal to our prediction plus some error. You can write it this way, or you can write it without the error and say the predicted y values with a little hat on it are going to be equal to that. So you predict something, but then there's error around it. So you can either add in the error term or else put a hat over the y. Okay, but this is not a parameter, so just ignore that error term. That's not a parameter. We're just estimating these betas. Okay, so what are we given here? That n is 35, and then I said, okay, I had to add these 2 other facts, that r is equal to 0.5, and the standard deviation of our y values is 10. So now we're supposed to fill in these missing blanks here. Okay, and the first thing that we need to do is get this total here, SST. So let's just think how we do that. So I'm going to go to the iClicker right now. And okay, so let's start this. And it says, okay, so you're given the standard deviation of the y's, n is 35, and r is equal to 0.5. So of those 3, which one is not needed to calculate the SST, the sum of the squares total? Okay, I'll just give you up to a minute, so because some of you are just walking in. Okay, so let's see. So most of you chose, which one's not needed? Most of you chose C, R. That's correct. That one's not needed. And let's see why. So R isn't needed because this sum of squares total is just a measure of the spread of those y values. It has nothing to do with how well the model fits. It's just it's the sum of the squared deviations from the average y. All right, and so that's how you would calculate it. It's just the standard it's just n times the variance of the y's, 3,500. In this case, 35 times 10 squared. All right, so now let's look at our next question here. And the next question is, so here's the model. And how many parameters are in this model? Just choose one of those. Okay, I'll just give you till 50 seconds. So. Oh, did I not go to the next question? What happened? Did it? What the? I am so sorry. What happened? So question 2 is right there. Did it switch back? Is that what happened? Yeah. How many parameters are in the model? Sorry about that. Thank you for pointing that out. Oh, when I clicked something, I guess it switched. Okay, so everybody's got their answer now, so I'll stop it. And let's see what you chose. And you chose 5 parameters, which is correct. Okay, so let's look at that. And it's 1 for each of these betas that we're trying to estimate, including the intercept. So there's 5 parameters in the model. Okay, so now let's go over to the document camera and fill in that table. So let's do that. And so this is just a sort of generic problem, and let's just make sure we understand how to do this. All right, so the sum of squares total, we just said, is going to go right there, and we just said that it's n times the standard deviation of the y squared. So in this case, it's 35 times 10 squared, so it's 3,500. All right, so we've got that. And now we can split up these this variation into 2 pieces. One, this is SST, right? And one is going to be r squared times SST, and the other's 1 minus r squared times SST. So what's r? We have to look at r, and r is 0.5. So r squared is just 0.25. So we're just going to take a quarter. 0.25 times 3,500, and that's 875. And 1 minus 0.25 times 3,500, that's 0.75 times 3,500, and that's 2625. Okay? So this is r, and r squared is just 0.25. All right, so now we want the degrees of freedom. So as we said before, the degrees of freedom, what are they going to be? Well, there's going to be, we have 5 parameters right here. The parameters is equal to 5. So the degrees of freedom is going to be, well, first of all, what do we have down here? We have, do you know how, maybe I should have you fill this in on your own for just a minute, just to make sure you know how to do this. Okay? Just take a minute to fill that in to make sure you know how to do that. Remember, this total one's always n minus 1. So that's going to be what? N is, where do we have n? Right there. Let's just highlight what we need here. So, okay, so we need this, and we need this to fill in these, all right? So the total, the degrees of freedom corresponding to sum of squares total, you just have, it's just one, you've already estimated the average, so it's n minus 1. N minus 1 here. So this is 35 minus 1, so that's 34. And then for the model, here, it's the number, the model has these 5 parameters, but basically this is already taken care of by the average, so it's just p minus 1. And this one's taken care of by the average, so it's p minus 1. So you just say that's 5 minus 1 is 4. And then they have to add up to 4 plus 30 adds up to 34. And this is n minus p. Okay? And then what you do is you just want to get, these are just the sum of squares total, and you want to divide these by basically, you want to take a mean of these basically. So you want to divide them by their degrees of freedom. This one is all the points minus 1. So you just divide 3,500 by 30. But we're not taking the average here. Sorry. We don't need to do that one. We're just going to, you see, what we're trying to do is get this F ratio, and F ratio is going to be the relationship between these two. The F ratio is going to be the square root of that one over the square root of that one. We don't need anything here. Okay, so we can just cross that out. All right, so we have 875 divided by 4. And then we have 2625 divided by 30. And we're just taking the ratio of those two. Okay, so we have 218.75 divided by 87.5. And that's 2.5. I mean, we could have done this. You sort of have too much information here. We could have done the same exact thing, we could have done by what? Getting 2.5, you could have done it. I wanted you to fill in this table, but we could have done it just just by saying, okay, that our F statistic, this is equal to what? R squared over 1 minus R squared times the ratio of what? N minus P, which would be over P minus 1. So in this case, what would we have? We would have 0.25 over 0.75 times the ratio of 30 over 4. So that's all we're doing. It's exactly the same thing because these sum of squares, when we did this, the sums of squares cancel out. And that's exactly the same thing. All right, so you can see that what we have is 2.5. Right? 1/3 of 30 over 4, 2.5. It's the same thing. Okay, so any questions on that? Any questions on that? All right, so then what are we this standard deviation of the errors is a measure of how the size of the errors around your model, right? And so it's just going to be the square root of that right there. So that's the square root of 87.5, which is 9.35. All right, and then I should have written the R squared down here. That is just 0.25. So it's sort of overdetermined. We have multiple ways of doing this when I give you this much information. Basically, when you have the standard deviation of the y's and R here. So now what do we do? All right, so now that why are we even doing this? Why are we doing this? This is a general way we're going to test the strength of this model to see if there's any significance to this model. It's an overall test to see if this has any predictive value whatsoever. All right, and so we get this ratio, this right here, this F. This is the important thing that we're getting out of here. This F statistic, which is 2.5. And what are we going to do with that F statistic? We're going to compare that. We know that this F statistic has this known distribution, and we're going to compare this to what we'd get if the null was true. If this really had no predictive value whatsoever, if all these betas, these slopes just weren't giving us any good predictive value, so we might as well just estimate the average of y, predict the average of y for all, no matter what those x's are. Okay, so we got this F, so we want to compare this right here. We want to compare our F statistic, what we actually computed, to what? To a critical value of F when the null is true, to the critical value at some significance level. So when the null is true, this statistic, this F statistic, has an F distribution depending on, there's many F curves, and so you have to look at the particular F curve that has 4 degrees of freedom in the numerator and 30 in the denominator. And then you'll get a value for that. And let's see if that's one of the ones that's on our F chart at the back of the book. If not, I'll have to give it to you, or we'll have to look on the computer. So now we need a significance level, so let's just say at 5%. So we'll look and see if that's one of our F stats. One of our lines on the table. And let's see if it is. All right, so what do we need? The degrees of freedom in the numerator is 4, and in the denominator, it's, so it's right here. Can you see? Can everybody see? I'm looking here for the degrees of freedom in the numerator, and this is at 5%. So I'm looking at this row, this column and this row, and right here is our critical value, okay? So we'll compare it to that. Which was compare our F stat to this one. And this was 2.69. And ours is 2.5. So we're comparing that. So 2.5 compared to 269. So do you think we're going to reject their null or not? We're going to let's remember what we're doing here. And this is at alpha equals 0.05. So I'm just going to sketch a curve here. And F here's 0. F is always positive, right? And so you have this curve. It's going to has a long right-hand tail. And what this critical value that we're saying when the null is true, if we compute this statistic, it's going to vary, right? It's going to vary. It's going to be around 1 when the null is true. That's going to be the mean. That's the expected value. But, it's going to have a distribution, right? Every time you sample, it's the sampling distribution of this statistic. And every time you're going to get a different F value. And when the null is true, you'd expect to get 1. But this value right here, 5% of the time, you're going to get this big an F statistic or bigger. So that's the critical value at 5%. So let's put that in. So let's just draw that. So that is 2.69, and that's our F star at 5%. So that means the probability of having a statistic, we got 2.5, having one 2.69 or bigger is 5%. That part's 5%. So we got 2.5, which is just short of that, right? So our F is right about here at 2.5. So, it's closer, but, it's on this side. So if we were going to be very strict about it, could we reject the null? We reject the null. Then it says most of the time you get on this side when the null's true. But if it's so weird and so unusual to get on this side, 5%, well, then we're going to reject this picture. Well, we didn't get, our statistic wasn't so extreme, so we're not going to reject the null. But it's pretty close. So, there's no sharp dividing line here, but strictly speaking, we would not reject the null. Does that make sense to everybody? Okay, so we'll just say we cannot reject the null. We'll just say compare. So this is less 2.5. R is less So our p-value is greater. So p-value is greater than 5%. So we cannot reject the null. We can say it's plausible that this model isn't doing anything. If we reject the null, then we say, hey, we got something in the model. All right? So cannot reject the null at 5%. I know a lot of you know this, and I'm just going over it again because people seem to have some problems with that on the homework. They weren't sure what it seemed like. They weren't quite sure about what this critical value meant. And typical values of the mean of the F distribution is always 1, no matter what the degrees of freedom are, very close to 1. So if you get really far from 1, you know that you can reject the null. And this just wasn't far enough. Does that make sense? Okay, so that's all there is to that. And let's move on. So now, what we were doing before was we were doing this example where we were predicting final exam scores based on homework and exam averages, midterm averages. And we found significance overall in the model. No shock, right? No surprise. We've been doing this, and we found that the overall chi-squared and F were both huge. Like, where was that? Right back. It was back when we were testing this model. It was 32.4. That's a huge F statistic, huge. And so we said the probabilities, the p-value is tiny there. The degrees of freedom were, this was the 107 students, and we were just using, the model was this right here. The final is equal to something times homework plus exams. So, and here was our chi-squared, 66.81. They're just both huge, and we said, okay, obviously this model's better than nothing, and it's no shock. Don't you think your midterms and your homework are going to tell you something about how well somebody does on the finals? All right, so our next step is, so we rejected the null that the model's not doing anything, and the overall there was tremendous significance overall. So our next step is what? Our next step is we're going to use, okay, so now we know that at least one of the slopes is significant, and so we're just going to see which one, maybe both. So we're going to go back to using Z and T tests for the individual slopes in the multiple regression model, and that's what we're going to do for the rest of the hour. We're just going to, this is going to be very familiar to you. So once we find that at least one of the slopes is significant, we can do Z or T tests on the individual slopes. Okay, remember these are not the same slopes as in the simple regression, right? Because they're taking into account all the other slopes in the model, all the other parameters in the model. Okay, all right, maybe I should highlight this just to make sure you understand this. The multiple regression slopes are called the partial slopes, right? Because they're the slopes that explain the part of y that's left after the other x's in the model have already done their part in predicting y, right? So they're only contributing their separate part. All right. Now, so if we found significance overall, now what we can do is we can test for the individual slopes in our multiple regression using a Z or T test. Remember, we can't do that for the collective effect, but we can for the individuals. So that's what we're going to do now. Any questions on that? We cannot use these for the overall when you have multiple slopes to the error. But now we're focusing in. We want to see, okay, we know, we're trying to see if homework significant, is exam significant, are they both significant, etc. All right, so let's do that. That's all we're going to do here. So the F-test told us that at least one slope, maybe both in this model right here, is significant. Which one? Let's test them. All right, so the null hypothesis is what? The null hypothesis is that, let's just start with the homework slope, okay? Is that the homework slope is equal to 0. You could also write that as if the homework slope of if homework was x1, we'd just say that beta 1 in the population, the Greek letter, is equal to 0. That's what H not saying, right? And then H alternative is saying what? It's saying that it's not equal to 0 in the population, which would be the same thing as saying that beta 1 is not equal to 0. All right? Any questions on that? Now, the null means that once you control for exams, knowing someone's homework score doesn't help you at all in predicting their final scores. All right? The small positive slope in our sample, even though we have this little slope that's positive, is just due to the luck of the draw. Okay? So even though homework alone is a good predictor of the final, by itself, it's good. We already saw that when we just did a simple regression. We saw that. It might not be once we add exams in there. All right? So that's the idea. So we're going to use the z-test or the t-test. This is a big sample size, 107. We could use the z-test. We'll compare it to the t. But let's just start with this. It's simpler. And we're just going to do our usual test. We observe an observed slope minus the expected slope over the standard error for the slope. Now, we're not going to have you compute these standard errors anymore because when you have these multiple x's, they're really tedious to compute. We just did it for a single x, but now when you have multiple regression, we're just going to let the software do it for us. It's just tedious. So that's what we're going to do. And so what do we have down here? So here was the overall chi-squared, that huge value. It's somewhat different than what we computed just because we did some rounding when we were doing it by hand. So this is what the computer printout said, but it's almost the same. And now this is what the printout gives us for, here's your intercept, beta naught, here's B1 and B2. Okay? And so what we're looking at right here, I erased this because I wanted you to find this z statistic and this p-value. So I erased the computer printout here. So we're just going to do that right now. And so it's just the observed minus the expected over the standard error. So let's just calculate z. So z is going to be equal to our observed slope, which is just right here. It's just, I'll highlight what we're doing, just saying this, that's what we saw. We expected 0 minus 0 over the typical amount the sampling distribution of the slope is. So that's the typical variation over 0.07223. Okay, and I did that, and I got 2.27. So that's what goes in here. All right. So nothing new there. And now we have to find the p-value. All right. So let's find the p-value. So we know it's normally distributed here. I'm doing a z-test. So as a z-score, we'd expect 0. Also, as a slope, we'd expect 0. The expected value of the slope is 0. Now, we got what? We got 0.1641, and we're just trying to figure out where on here it is. We know it's positive here. We just want to know. We know the normal curve looks like this. 1, 2, 3, negative 1, negative 2, and negative 3. But we're in these units of final exam scores per homework score point, final exam point per homework point. That's what the units are here. And where does that fit in on here? This says it raises your final exam score by, on the average, by 0.1641 points for each increase in homework for people who have the same exam scores. So if you take two people who have the same exam scores, each extra homework point average will raise it by that much. That might be just small and just due to random variation. But here we see what the random variation is. It's only this much. So we just want to see where that lines up on here, and that's what this tells us. It tells us how many standard errors is, and it's 2.27. So now we know where to place that. This right here is 2.27 as a z-score, and as a slope, it's 0.1641. So it's pretty far out there, very far out there. Okay? So this is, as a z-score, it's 2.27. That's our z. And as a slope, it was that. All right, so now what we want to know is the p-value, and the p-value is going to be this area if our alternative hypothesis was one-sided, or it would be the area between what? If it's two-sided, then we'd have to take into account both tails. First, we have to find out what this middle area is. So between 2.27 and negative 2.27 on the normal curve, we get about 97.7, let's say. So that's 97.7 in the middle here, between 2.27 and negative 2.27. All right, so it looks like, well, it was two-sided up here, but you know what? I was pretty sure that homework was going to help people. Wouldn't you think that reasonable alternative hypothesis would be that homework would, the higher your homework score, the better your final exam score would be, rather than the worse? So let's say we had a one-sided hypothesis. We can do it both ways. But for the one-sided hypothesis test, then this would be our answer right here. So for the one-sided alternative hypothesis test, that would be what? The beta 1 in the population, the slope for homework is not, what's it going to be? Greater than 0, right? And then our p-value would be what? It would be 100 minus 97.7 divided by 2. Okay? And that is what? 2.3 divided by 2. So that would be p equals 1.15%. For one-sided. So this is 1.5%. If it's two-sided, we'd have to say, okay, we don't know if homework helps you or hurts you. We just know it's not neutral. It does one or the other, and that's what our hypothesis would be, and then we'd have to count both tails. So for the two-sided, if you were doing that, you're going to get a bigger p-value. And then you just have this hypothesis that beta 1's not equal to 0. And then it's just your p-value is p is equal to 100 minus 97.7. It's just the whole 100 minus the middle chunk. It's just those two. You don't divide it by 2. So that would be equal to 2.3%, twice as big. And this was equal to 1.15%. All right, so that's the idea, and So we mark Z and P. So it would be 1.5 on either side. And that's the idea. And either way, we'll reject the null at 5%. So our conclusion would be we'll reject the null and conclude what? Conclude that homework is significant. That the homework is significant. We should keep it in the model. It's significant even for a two-tailed test. If it's significant for two-tail, of course it is for one-tail, because that's even half the p-value. So it's even for two-tail, even if they were asking for a two-tailed hypothesis, even for a two-tailed test. All right, does that make sense for people? So this is a review of what this basically what you've done before. All right, now, as you can see, homework's even more significant. Look at that. I mean, not homework, exams. Exams are even more significant. And that's no surprise, right? All right, so now you want to do a t-test. I can just show you the difference. It's very similar. We're going to get something very similar. So we'll just do the t. All right. So, all right, so again, it's very, very similar. The t is going to be the observed slope, which is the same slope that we had in our model, the same exact thing, minus the expected slope. We're just going to have a slightly bigger standard error here, slightly bigger by a factor of n, 107, square root of 107 over 104. That's what we're going to do. So it's just going to be slightly bigger. You can compare them. Here you have 0.07327, and here we had 0.07223. So it's big. So it's slightly bigger by a factor of the square root of 107 divided by 104. All right, so that's one difference. But the bigger difference is going to be, well, the bigger difference is, there's also a difference that the t-curve has fatter tails. So there's going to be a bigger p-value because it has fatter tails. But it's not going to be very different because our degrees of freedom are 104. And the t-curves are going to look very much like, the t-curve is very much like the normal curve by the time you have that many degrees of freedom. So it's not going to be that different, but we'll get a slightly bigger p-value, but we'll still reject the null. So we can go through it. So now what's the difference here? Okay, so we're looking, and so you right away see that you have to deal with these degrees of freedom, right? And that's n minus p. Now that's really different. Okay, so let's read this. This is important. So the degrees of freedom in the model are the same as in the denominator of the f-test. Note, the t-test for individual slopes in multiple regression takes into account all the other parameters in the model, so you need to adjust the degrees of freedom accordingly. It's not n minus 1, it's n minus the number of parameters, right? And before, when we were just doing t-tests before, remember we had n minus 2, right? Now we're going to have what? N minus 3, because we have 2 more parameters. Does that make sense? And when you did a t-test on the mean, it was just n minus 1, because there's 1 parameter. So it's just t-tests are going to adjust always to all, because what's happening is you're taking into account all the other variables in the model. So you can't have the same degrees of freedom as if you just have one slope, or if you have, does that make sense? All right, so you just need to remember that. So we have 3 parameters here. You can see, here's our 3 parameters. We have that same model, the intercept, and here's here they are again. And what are we going to do? We just want to find t and p. So we're going to calculate t. We'll just do exactly the same thing. So what's t? We're just going to use these right here. It's exactly the same thing. So our observed slope minus our expected slope over our slightly adjusted standard error. And we get this is a little bit bigger, so our t statistic is just a little bit smaller. Before we had a z of 2.27, now we have 1 of 2.24, okay? So so it's slightly, so you can say t stat is a little bit less than the z stat. Okay, that's what it is. All right, so now what are we going to do? We don't have a normal curve anymore. We have a t-curve. So you have to remember there's a whole family of t-curves. So which one are we going to use? So we need to use the one that has degrees of freedom equal to 104, which is n minus p. I need 107 minus 3 parameters. That's where that comes from. So you have to look at that. It's going to look very much like the normal curve. So now we have this t and the slope. I'm doing exactly the same thing we did before, but just with it, and it's centered at 0. And the slope, the expected value of the slope is 0. Now we want to see where to place this tiny little slope on here. Okay, where to place it on here. And we see that's where we're supposed to place it, at 2.24. So this, let's say this was 1, this was 2, this was 3. I drew the curves. You can't tell the difference, but this is supposed to have a little fatter tails than the previous one. And this is a tiny bit smaller. So, but that's not really, remember, I could have used this SE plus for the Z curve. There's nothing special about this SE plus. It's a better estimate when you don't know the standard deviation of your sample, this is a better estimate, okay? But when you don't know the standard deviation of the population is what I meant. But we just don't bother to do that, because by the time you have a big enough sample size that you can use a Z, this hardly matters. So this part of it, we could have used this statistic for the Z just as well, just people don't do it. All right, so we get that. And, but now we have to look on a t-curve. So here we are at this right here is 2.24. Okay, that's our t is equal to 2.24. And that translates, again, into a slope equal to 0.1641. And this is the area that we want to figure out right here. And this curve is a little bit fatter. So this p-value, instead of being 1.15, it turns out to be 1.36%. That's your p-value right here. And since there's so many, I had to look on a, 104 is not in the back of our book, so I had to look on the computer for this. Okay? We want to look at the t-curve with how many degrees of freedom. So we have to, this is a t-curve right here, supposedly, with degrees of freedom equal to 104. Okay? That's what we're doing. So is the p-value using the t-test always bigger? Yes, it is. It's always bigger, just because of the shape of the t-distribution. But it's not very much different. So any questions on that? All right. Now, confidence intervals. How do they compare to this? So you could do these confidence intervals the same way, Z and T confidence intervals here, but you just have to be careful. Again, you'd have to use the critical values for T associated with the degrees of freedom of 104 here, and I did that, and notice these are a little bit bigger. These critical values are bigger, even though the t itself, the t stat, is always smaller, the critical values are bigger. It's really just they're bigger because you have to go further out. What are these critical values? Well, they're just, why don't we do this one with this curve? Because here's a t-curve for the same one. So what this is saying, this 1.983, is saying that if between 1.983, so if we, it's saying, maybe I could just draw it right in here. So I'm just looking at this right here, these critical values. And we're doing like right here, 1.983. Well, they're all 1.983. What they're saying is between 1.983 and negative 1.983 is 95% on this curve. I don't know if it might be confusing if I draw it in. I'll draw it in like this. All right, so this is the critical value, t star, equal to 1.983, and this is negative t star. Okay, and between those two, that's 95%. And then, but between our actual t and negative t, it was much bigger than 95%, you see? So that's the idea of these critical values. So basically, remember the question, do our confidence intervals agree with our significance test? Yes, they do. Because look, 0 is not included in the confidence interval. 0 is not included in the confidence interval. I could do the same with the z-curve. So with the z-curve, maybe it will make, it's just easier to draw it here. Okay. So now what does this mean? It's saying that 95% of the area of the curve is between what? Basically 2 and negative 2. It's not quite 2. It's a little bit smaller than 2. It's right there. It's z star and z star and negative z star. It's the same thing. That's equal to negative 1.96, and this is equal to positive 1.96, and that's 95%. And we had our z-stat was bigger than that. Our z-stat was equal to 2.27. It was bigger. So we rejected the null at 5%. 95% means this is 2.5%. Hold up, I just want to get the highlighter. Okay, so here, this is 2.5%, and this whole thing is 2.5%, right? It adds up to 100. Now, when we rejected the null before at 5%, let's say it was for a two-sided test, that meant we were in this region. And that's the exact same thing as saying our confidence interval doesn't include 0. Because when we're outside that region, if we go 1.96 times the standard error in either direction, we don't include 0. So it's equivalent. So do they agree? Yes. Because our 95% confidence interval, either one of them, does not include 0. Look, they don't include 0. 0's on this side, right? So that's the same thing as rejecting the null. That's the same as, it's equivalent to rejecting the null, that our slope is equal to 0. We're saying it's not equal to 0. Rejecting null, that slope equals 0. for a two-sided test, right? At alpha for two-sided alternative. At alpha equals what? Together they add up to 5%. At alpha equals 5%. It would be for a one-sided. Okay, that's just equivalent. All right? So what are we looking at? We're looking at these confidence intervals don't include 0. All right. And this, you might want to note that the critical value of t was equal to what? It's equal to 1.983, which is greater than the critical value of z, which is equal to 1.96. Because you have to go further out. These tails are fatter, right? It's lower in the middle. Whoops, for the t. So you have to go further, for the t, you have to go further out. This is the z. Well, our t is fatter in the tails, so we have to go, it's lower in the middle. So to get the 95%, we have to get a little bit further out, to not to 1.96, but to 1.983. Because it's a little bit shorter and fatter in the tails, and it still has 100% of the area. All right, note that even though, but don't get confused with when we computed our t-stat, because we used SD plus, our t-stat was equal to 2.24, which was less than our z-stat, which was equal to 2.27. This is just because we use SE plus. We could have gotten the same statistics here. This is the more important difference. Okay, any questions on that? All right, now, so no questions at all? All right, yeah, oh, a question. I get so happy when there's a question.
What do you say the 95% CI does not include 0?
Yeah, the 95%, where did I write that? Oh, yeah, that's all crossed out. This is the most important thing. I didn't mean to have it crossed out. I wrote that first. Yes, because our 95% confidence interval does not include 0. You see, 0 is not inside there. Imagine if we landed like right here. Then if we went 1.98, if we landed in here, closer to 0, it would be. Do you see? Well, oh, do you know what they're doing, how we're getting this confidence interval? What we're doing, I'm sorry, maybe you don't know. We're saying we're taking this, right, for both of them, and we're saying plus or minus this times your standard error. And that's how we get, so to get this number, we'd say 0.1641 times 1.983 times that equals that. Okay? If there's a 0 inside here, pretend this was smaller. If it was smaller, then it would include 0. If it includes 0, that means that we're really closer to 0. We can't reject the null. We could have a 0 slope. That's all it means. Okay? So the idea is, I'm sorry, the way that you get these, think of this as plus or 2. So you just take your slope plus or minus 2 standard errors in either direction. So that's where it matches up to this. Good question, because we went over confidence intervals before, but I forgot to mention that. Does that make more sense to people now? Okay. So what are we saying with a 95% confidence interval? We're saying we're 95% confident that the true slope for the entire population is within these limits. right? We're 95% confident that the true slope, this is the slope we're estimating, right? And we got from our sample, and we're 95% sure it's in those limits, and those limits are outside of 0. So that's why we reject that the slope's 0. Does that make sense? And same with that. And if 0 was inside here, then we'd be saying, okay, we're 95% sure it's within this limits, and we're 95% sure that 0's in there. So of course we couldn't reject. Does that make sense, Joe? Yeah. Thank you. Any other questions? Yeah, another question. Oh, I get to walk around because I can't hear. That's even more fun. Go ahead. Oh, I didn't do anything with the exam slopes. No, I didn't. Yes, I should check the exam slopes, and we can see. Let's do that. Let's check this exam slope because it's done for us. It's done for us. And look what we have. We've got, it really doesn't include 0. It's not even close to including 0, right? So these are, it's a bigger slope, and the standard error isn't that much different. So this is really significant, and as you can see on the previous page, look at the exam's z-score, 6.321. Wow, let's look at that. 6 on the z table, on the normal table, it's off the charts. That means if we were going to try to get its p-value, that's 6, 1, 2, 3, whoops. Here I am. Let's say I was testing this. I'd look at 6.321 on here. So a slope of 0.5, I'll draw another picture. So for that, what would it look like? Well, you'd have the normal curve, right? That doesn't look like a normal. Here we go. I got to put this up here. All right, so you got the normal curve. And that's 0 as both a z and a slope. And we're talking about exams now. And now this is telling us right here that the exam has a z-score of 6.321. So that lines up, 0.5824, lines up where? Whoa, you'd have to go 1, 2, 3, 4, 5, 6, whoa, way over there. That's where the exams would be. That would be the 6 as a z-score. It was, oh, I'd even forget what it was now. It was 6.3 something, right? Yeah, it was. God, these decimals drive me crazy here. Can't even remember them. The exam score, the z-score was 6.321. Oh, 321. How come I couldn't remember that? That's easy. 321. And that would line up with this. It doesn't look so big. It's 0.5824. And that would be almost, the p-value would be that would be just basically 0. Does that make sense? And I say it doesn't look that big, but it is big. What does that mean? It means that for each additional point on your exam score for some, let's say take 2 people who have the same homework average, and one of them has 1 higher exam point average. That means we could put on the average, their final exam score is 0.5824 higher. So almost 6, so that would mean 10 points higher would be 6 points, about 6 points higher on the final. That's much bigger effect. Okay? That's what's going on. And now we're going to look at model building. And there's whole courses on model building, but we're just going to say, we're just going to try to give you an intuitive feel here on this page. So now we say, okay, we decide that both those slopes are significant, so we're going to keep them both in the model, the homework slope and the exam slope, right? Maybe we could do even better by adding on lab scores. So this data was taken from when Stat 100 had labs. Okay? We didn't have such giant classes, and we were able to have labs. So people worked on the data program. And so we have a lab score as well. So we're going to see how adding a third variable to the model, what that does. And this is what you do. I mean, this is what you'll be doing all the time when you try to build models. You say, okay, we've got a good fit now. Let's see if we can make it even better by adding another variable. So how do we assess whether it's better or not? That's what this is beginning to try to look at. All right, so Z and T test showed that both the homework and the exam slopes were significant in the regression equation in this. I'm wondering if adding a third variable would significantly improve the prediction. So this is going to be an iClicker, so think about it now. I'm just going to put it right up. I added labs as a third variable. How do you think that would change R squared? So let's put it up. Let's look at it. And let's think about it. So our next one is this. Okay, so I added labs as the third X variable. How do you think that would change R squared? So you have to think R squared. What is R squared? It's the correlation between your predicted values of the final and the actual values. All right, so if you add another variable, how would that improve your predictions? So the first says so decide which one. R squared may go up or down depending on how labs is correlated with finals in the other two variables. R squared has to go up or stay the same. Adding a parameter to the model can never make R squared go down. So think about it. If you add another predictor, could it make your predictions worse? Okay, think about it. Choose A or B. I'll stop it at 55 because we have to get, okay. All right, and let's see what you chose. It may go up or down. Wrong. The answer is B. Okay, R squared has to go up or stay the same. Adding a parameter can never make it go down. Why? Think about it. Adding another parameter can't make our predictions worse. Why? If there's any correlation between our variable, like in this case labs and finals, if there's any correlation at all, the prediction has to improve. Whether it's positive or negative, it still gives us a better prediction, right? So if there's any correlation at all, it will have to improve. If R is 0, if the labs have nothing to do with don't give you any predicted value, then R squared will stay the same. It can't go down. Okay? It can't go down. So, does that make sense? How could your predictions get worse when you add something? You're adding more information. Either the information is irrelevant, in which case your predictions are going to just be the same, or it's, if it's positively correlated, of course it's going to go up here. If it's negatively correlated, you have more information, so of course it goes up too, right? Yes?
So are there any ways to make our prediction worse?
Not by adding a parameter. It'll always make your predictions better. It might not make your predictions better for the population, but it makes the predictions of that sample better. So how do we define? We can't use R squared then, because it will always go up. So we have to watch. You'll see what happens. So we'll go over to, let's go to the document, Karen. But what you're absolutely right. We don't want to just add tons of predictors. That's not going to make a better model, even though it does make R squared go up. So let's look at this. So, okay, so adding a parameter can never make it go down. Because why? If R between, let's say the third parameter, the third variable, and Y is not equal to 0, then r squared, by definition, has to go up. And if r and x then r squared will stay the same. Okay, so I checked r squared. Here's, can you see this? Maybe I should zoom in a little bit. Model building is kind of fun because you get to say, oh, is it, what's happening here? Okay, so I checked r squared, and it went up a tiny bit. Look at this. A tiny bit. Just a tiny bit. Okay? Does that mean that lab significantly improved my model? So here's the model with 3 parameters. This has parameters equal to 3, and this is when I added the labs, and I have parameters equal to 4. Now watch what happens to F. Look at F. F went way down. Why? You see, so you can look at the F stat, and you can get a p-value. Your p-value is going to go way up. Why? R squared went up, but F went down. So the question is why? Let's think about it. Well, let's compute it. So remember what F is. It's R squared. It's R squared over 1 minus R squared. So here it's going to look like this. Let's just do that part. And here it's going to look like what? You have a bigger R squared, but you're going to get a smaller F. Watch. Here you're going to get a bigger, if you look at R squared over 1 minus R squared, yeah, that's a little bit bigger. But look what happens. You have to multiply, basically, you're going to multiply here by 104, and here, and divide by 2. And here, well, this won't change it that much, but look, you're dividing by 3 here. So every time that's that, adding that extra parameter costs you a degree of freedom, which means on the F distribution, this is going to be a much lower F and have a much bigger p-value. So this one turns out to be that, and this one is that. Okay? Does that make sense? Maybe we should write that down. So does this mean significantly? No. What does it mean? Let's go down here because this is a very important point. Let's write it. I don't have room there. So let's just write the idea behind it. No. Each time you add a parameter, you're going to, each time you add a parameter to a model, R squared will go up or stay the same, right? R squared will go up or stay same. It will never go down. But, and this is a big but, it costs you a degree of freedom. And degrees of freedom, you have to pay for those degrees of freedom. It's like you're adding another bucket to, like, let's say random rain's coming down, right? And you're adding another bucket. Of course you're going to catch some more rain, but is it just scatter? Are you really explaining anything? Are you really you're just catching random scatter? Or are you really improving the fit? I can't. Okay, but it costs you a degree of freedom. But it costs you a degree of freedom. That's what that says. It costs you a degree of freedom. So R squared has to go up enough. So R squared has to go up enough to make it worth it. So F measures that. Can you see what that says? That says F measures that. But it costs you a degree of freedom. So R squared, you want your R squared to go up enough to make it worth it, and F takes that into consideration. When you can look at, so you want to look at your F statistics and your p-value, that will tell you, okay? That's if you're comparing models that have different numbers of parameters, okay? If you're comparing models that have the same number of parameters, then R squared going up will be important. Okay, it will always correlate with a higher F. All right, let's just see now something. Now, R squared did not improve enough to warrant adding the third variable. Labs is not significant, as you can see above. Where is labs? Labs is not significant. See, like right here. Look, neither of them are significant. Look what happened when you added labs. When we added labs, both the homework and the labs are not significant. Whereas here, it was significant. So how did that happen? Labs is not considered, but why did adding labs make homework change from being significant before to non-significant? How could that have happened? So what it is, I say, could this be a mild case of our left foot, right foot syndrome? You have to be very careful if you add two variables that are highly correlated. Let's check the correlation matrix for multicollinearity to see if labs and homework are strongly correlated. And look at them. They're very strongly correlated. So that is lousy. That means that both slopes can become significant when both are included, even though. Okay, it doesn't mean we should throw them both out of the model. All it means is we can't do a good job of estimating how much of the prediction should be based on one or the other, because they're both predicting just about the same thing. So it just, what our coefficients, yeah, so it just, those coefficients don't make very much sense when they're both predicting pretty much the same thing. It's just fitting the random stuff in our model and doesn't have, you know, if they're predicting exactly the same thing, then any linear combination of the two of them would work. Yeah? Yes. It should be 103. Thank you. Is that what you said? Yes. That is way better. Yes, I'm so sorry. Excellent. Thank you for catching that. Definitely. Okay. 103 over 3. Thank you. So, anything else? I think that's, I thought we were going to finish the last section, the last page, but we'll do that next time. Thank you so much for asking questions.